In this video, we're going to be looking at the line of best fit through a scatter plot. We're going to use technology to find that line of best fit. We're going to interpret the R value, what's called the correlation coefficient for the regression, and we're going to estimate that correlation coefficient, again R, by looking at the scatter plot, and we're going to use a linear regression for what's called interpolation and extrapolation, which will make more sense later, I promise. Just hang it there. So let's look at what a line of best fit is to begin with. It's just a line through the data of a scatter plot that is as close as possible to each point. So if we look at our scatter plot right here, we see that there is this trend. It almost feels like something like that is going on through the data, that there is a line there. If we're looking at the line of best fit, what we want to find is the exact line that makes all of those as close as possible to the line. And when we're doing this, quite frankly, you want to use technology on this. There is exactly zero reason not to use technology to get this line. Yes, it can be done by hand. Nobody actually does that anymore because our calculators have gotten so good at it that through a process I will show you a little bit later on in this particular quiz cycle, your calculator will give you the equation of that line. And so the equation of this line right here would be y equals, and notice up here it says ax plus b. A is 30.088. I'm just going to round that off to 3 places past the decimal point, times x, and then b, our y-intercept, is negative 159.474, and so there I have from my calculator that exact equation, and then I can plot that exact line, and we can find our line of best fit. So that's what we're going to be looking at doing during this time. This process where we get this line of best fit that models our data is called linear regression. So linear regression is just this whole process by which we build a model that is a line that represents all of this data. So rather than talk about all this data with all its warts and bumps, I can talk about this line, and that's just as good as talking about the data. Now, some things you have to clear up. Because the data is scattered all about this line, our predictions and such that we make with this line will not be 100% accurate. But they'll be pretty darn close, and we can determine how accurate they're going to be, how much we can trust them. And so we can just simplify our lives by thinking of this data as a line rather than all of these scattered dots that are kind of all over the place. So when we do a linear regression, we have two things that we get out of this that are very useful. The first of these two purposes of linear regression is to describe the quality of the relationship between the variables. And to do this, we use what's called the correlation coefficient, R. So if you look over here, you see this value of R equals 0.958, blah, blah, blah. This is called the correlation coefficient, and it tells us about the relationship between the two variables, x and y, or whatever our variables happen to be in each example. We also can get the equation of the line of best fit. So that's the y equals 30.088x minus 159.474. And we can use that equation to make predictions. And so now we're going to look at each of these two uses and kind of dive a little bit deeper into them. So first up is the correlation coefficient, R. That describes the nature and strength of the relationship between the two variables. And R will range from being -1 to +1. Now note that on your calculator there is a value of R squared. That is not the one we are looking at. We are looking for just R. We'll talk about R squared later on in the class when we get to quadratic and exponential regression. But for right now, all we're interested in is just plain old Jane R. And it again ranges from -1 to 1 with 0 in the middle. And you can see from this graph, or from this picture rather, what they look like. The closer the number is to 1, the more they'll line up on a perfect straight line. So if your correlation coefficient is R, then your scatter plot actually forms a straight line. There's no error in there. And then the closer it gets to 0, the more fuzzy it gets, the more it doesn't exactly match up with the line. You can see at 0.8, there's still, even though that's a very terrible line that I drew there, they're still very much close to the line. But at 0.3, they're spread out quite a bit. And when you get to 0, that means there's no correlation. There's no line I can draw through this data that makes any sense whatsoever. And then over here for negative correlations, you can see as the number gets closer to 1, that tightens up a little bit. So there are two parts to R. There's the sign, which tells us the type of correlation. So if the correlation coefficient R is positive, that tells us that there is a positive correlation, just like we talked about in the last video. If R is negative, there's a negative correlation. So we can see, looking over at the calculator for this data that we input earlier, that R is positive, and so this is a positive correlation. And then we have the number. The number tells you the strength of the correlation, and the closer that number is to 1, either positive or negative 1, the stronger the correlation. And if that number is 0, that means there's no correlation whatsoever. We also have the line of best fit. So remember, R tells us about our relationship. So looking at this, there is a relationship between temperature, and even though it's not labeled here, this is sales of ice cream. And when R tells us that there is a positive correlation, the fact that R is 0.957 tells us that that correlation is a pretty tight correlation. It's a good fit. So we can now use this to make some predictions. So for example, 1, how much ice cream would we expect to be sold if the temperature was 21 degrees? And then we do it again for what if the temperature was 30 degrees? So the first thing we need to do is write down our equation of the line of best fit. We can round this off to the thousandths place. It really doesn't matter if you round to the hundreds or the thousands, but we'll agree to do to the thousandths just so that we all get the exact same answer. 474. And now what we need to do is we need to take a look at these variables and kind of realize what each one of these variables means. X is what's represented along the x-axis, and X represents the temperature. So I have to keep in mind that when I'm talking about X values, I'm talking about a temperature. Y, again, I unfortunately cut off the label here, but this is ice cream sales. So we want to know how much ice cream, that is, what is Y, if our temperature is 21 degrees. Well, remember, temperature is X, so this is saying, what is Y when X is 21? And all we have to do in order to find that is to substitute in for X 21. And that's it. Nothing more complicated than that. And then I need to input that into a calculator, which fortunately I have a calculator right over here. So let me clear out this data here. Hello, calculator. Thank you. And now I can just type in 30.088. 8. There we go. I apologize for the technical difficulties there. Times 21 minus 159.474. And now, through the magic of the calculator, I know that my ice cream sales will be 472.374. So let's talk about that number for a second. If I look at this graph and I plot that point right there, that at 21 degrees, notice at 21 degrees, very cleverly, there is nothing left there. So this question was well planned. But at 21 degrees, we're expecting about 472, something right in there, dollars worth of ice cream sold. So notice how that fits right in the trend. That dot right there is expected. That wouldn't be too out of the ordinary. And do note that that is an estimation. There's no guarantee that if it's exactly 21 degrees, we're going to sell exactly $472.37 worth of ice cream. However, it's a good guess. We can say that since this correlation is pretty tight, there would be no surprise if the range of ice cream we sold was somewhere between $450 and $500. So combining this information with R gives us a pretty good idea of about how much ice cream we can expect to sell if the temperature is 21 degrees. Now, something else I want to point out to you, this won't be tested, but it's good information to know, that this 21 degrees that we're looking at is within the data set. This is called interpolation. So interpolation is when you make a prediction about an unknown value within the data set itself. We're going to look at now what happens if the temperature is 30. Well, that's well outside our data set. That's over here somewhere. That is called extrapolation. So in extrapolation, we're assuming that our trend will continue unabated, and we're trying to find what would happen if that is true. So it's a true prediction of future or unobserved events. And so in order to do this, it's exactly the same as we did before. We want our temperature to be 30, so we would substitute that value in. And then, through the miracle that is the modern calculator, we can simply calculate this up. So if I clear out my data and I want, you know what, actually if you hit second enter, it brings up the last thing you typed in, and I can simply replace that 21 with a 30. And so I would predict, if this were the case, that I would sell somewhere in the neighborhood of $743 and roughly 17 cents worth of ice cream. And so this is extrapolation, predicting outside of the range of the data. And there you go. This is what a line of best fit is for. It tells us about the relationship and how good it is. That's the correlation coefficient R. And then the line of best fit allows us to make predictions about values, either interpolation or extrapolation, using that equation.